Hello everyone. Today we will see replay attack detection in IP security using sequence number based prevention with RFC 4303. In this we will see what a replay attack is, how attacker misuse captured packets, why normal authentication alone is not enough, and how IP security prevents replay attack using sequence numbers and sliding window mechanism. First, let's understand what is replay attack is. A replay attack happens when an attacker captures a valid network packet and sends the same packet again later. The attacker does not need to change or decrypt the packet. Simply copying and retransmitting it is enough. Because of the packet still contain valid authentication data, the receiver may think it is fresh request. This becomes dangerous because the same operation can be executed multiple times without sender's knowledge. Let's see some real-world impact of replay attack includes duplicate bank transaction, unauthorized access or session hijacking, repeated execution of commands, and corruption of system data due to duplicate updates. So replay attack are dangerous because even though the packet is original and authentic, it is reused maliciously by attacker.
The IP security uses HMAC-SHA256 to protect packets. HMAC creates a secure signature using the packet data and a secret key shared by Alice and Bob. If any changes the packet, the signature fails and Bob rejects it. But HMAC only proves the packet came from Alice. It does not prove the packet is fresh. So if an attacker replaces the exact same packet, the HMAC is still valid and Bob may accept it again. That's why IP security also uses sequence numbers for replay protection. In the next slide we can see attack scenario. Here Alice is sender, Bob is the receiver and Darth is the attacker. The Darth silently copies the Alice packet while they travel through the network. Later he replaces the same packet to Bob. Because the packets still have valid HMAC signature, Bob may process them again. This can lead to repeated logins, duplicate transactions, and replay attacks.
So about the code, we are using only Python standard library, HMAC-SHA256 OS, no external packages needed. These are our simulation settings. Window size is 64, which is the RFC 4303 default. The shared key simulates what I key would produce in a real IP security handshake, and we have Alice and Bob's IP address too. Here's the crypto. Compute HMAC uses Python's built-in HMAC.new with SHA256. Notice verify HMAC uses HMAC.compare digest instead of regular equal signs. That's to prevent timing side channel attacks. The comparison takes the same time whether it matches or not. Packet holds the SPI security parameter index, the sequence number, payload, and the HMAC tag. The bytes method packs everything into a deterministic byte string using struct.pack for the integers. That's what gets fed into the HMAC. The sign method sets the tag, verify, recomputes, and compares. Alice generates a random SPI using os.uRandom at startup, simulating I key negotiation. Every time she sends a packet, her sequence counter increments by 1. It never goes backward. Darth has two methods: sniff, which just appends the packet to his list, and replay, which sends it back. Notice replay doesn't touch the packet at all. Same byte, same HMAC, that's the whole point. This is Bob without protection. He checks HMAC. If valid, he accepts. That's it. No sequence number check. This is the vulnerable version. This is the important part. Bob has two state variables, self.high, which tracks the highest sequence number seen, and self.seen, which is a set of all sequence numbers received in the current window. Let's see how the code works. First, the program asks for the packets Alice will send. Type a login transfer and a logout, like a basic banking session. Then type done and the simulation starts. Let me do it. Step 1 is the I-key handshake. Alice and Bob agree on a security parameter index. You can see it is randomly generated. And they share a secret key. This happens before any data is sent. Darth quickly gets in between Alice and Bob on the network. He is not blocking or modifying anything, just silently listening. Neither Alice nor Bob knows he is there. Alice sends her login packet. Sequence is 001. You can see the payload and the HMAC tag generated for it. Darth copies it in the background. Bob verifies the HMAC, accepts it, and marks sequence is equal to 1 in his window. Alice sends a transfer of $500. Sequence number moves to 002. Darth grabs a copy again. Bob accepts it and the window now shows 2 ticks. Alice logs out. Sequence 003. Darth captures this too. Bob accepts it. Session is over from Alice's side. Everything looks normal. Alice disconnects. Now look at Darth's capture buffer. He has all the 3 packets with their original HMAC tags still intact. He didn't crack anything, he just recorded what was already on the wire. Darth sends all 3 captured packets back to Bob. Watch the output. HMAC OK accepted, HMAC OK accepted. All 3 go through. Bob cannot tell these are replay because the HMAC is still valid on everyone. Darth just re-authenticated as Alice and re-executed the transfer without knowing the password. This is the vulnerability. HMAC alone cannot detect replayed attacks. All 3 replayed packets were accepted. You can see the $500 transfer was executed a second time. Alice has no idea this happened. This is the problem with relying on HMAC alone. Now we give Bob the sliding window protection from RFC 4303. His window is already loaded with sequence 1, 2 and 3 from the legitimate sessions. All 3 slots show a tick. This is Bob's memory of what he already processed. Darth tries the exact same attack, same 3 packets, same HMAC tags, same sequence numbers, but now replay detected, dropped, replay detected, dropped, and replay detected, dropped. Bob checks each sequence against his window, finds it already marked as seen, and drops it every time. The sliding window catches every replayed packet. 0 out of 3 replayed packets accepted. Window state is unchanged. No commands were executed. Darth's attack failed completely. The final summary. The only difference between part 2 and part 3 is that one sliding window. That is what stops the entire attack.
Now I'll explain the prevention part. RFC 4303 solves replay attacks using a sliding window mechanism. Bob keeps track of the last 64 sequence numbers received. When a packet arrives, Bob checks whether the sequence number is too old, already seen, or completely new. If it's old or duplicated, the packet is dropped immediately. If it's new, the window moves forward and accepts it. This is important because HMAC only proves the packet is authentic, but the sliding window proves the packet is fresh and not replayed. Together, they provide secure communication. In this code, Alias generates packets with increasing sequence numbers, while Darth acts as the attacker who captures and replays packets without changing anything. Vulnerable Bob only verifies HMAC, so he accepts replayed packets. Secure Bob, however, stores previously seen sequence numbers and detects duplicates instantly. During the demo, Alias sends normal banking commands like login, transfer, and logout. Darth captures all of them silently. Later, he replays the exact same packets. Vulnerable Bob accepts every replayed packet, showing the attack succeeds. But when we switch to Secure Bob, every replayed packet is rejected with a replay detected. So the final result is clear. Without replay protection, attacks succeed. But with the RFC 4303 sliding window mechanism, all replayed packets are blocked successfully. Thank you.